Now I am going to discuss Fleming's left-hand rule. Before starting Fleming's left-hand rule, first we need to understand the direction of the magnetic field, right? So this is a page, or this is the board. So in this page, how many direction of magnetic field we can represent? See, this is the east, this is the west, this is the north, this is the south, or this is the right side of the page, this is the left side of the page, this is the up side of the page, this is the down side of the page. Apart from these four direction, there are two other direction, that is, into the page or out of the page. Into the page means, the magnetic field is into the page, and out of the page means the magnetic field is out of the page. So by cross and dot we can say this is the into the page. We can normally represent the arrow direction. The arrow direction means if you see the back side of the arrow, you will just see the cross side. So arrow is into the page, then if you see the back side of the arrow, just cross section of the back side, then you will see the cross. And when the arrow is coming out, or magnetic field is coming out, arrow is coming out, if you see the head of the arrow, so you see the cross section of the head of the arrow is only dot. So dot means the magnetic field is coming out from the page, and cross means the magnetic field is into the page, right? So in many cases, not only the magnetic field, sometimes for the current, sometimes for any vector direction, we use this cross or dot sign. So we understand there are 6 direction of the magnetic field, right? So right, left, up, down, and into the page and out of the page. Now let us try to discuss Fleming's left-hand rule. For this Fleming's left-hand rule, we need to take these 3 fingers. First is the forefinger. Second is the this is the first finger or forefinger, and this is the second finger, and this is the thumb, right? So first finger means what? This first finger represents the direction of the magnetic field. So it's the direction of the magnetic field, and this within this magnetic field, a charged particle is moving in this direction. You know, the direction of positive charge is called the current. So we can say this is the direction of the current. We can say this is the direction of the positive charged particle. So when these positive charged particles are moving in this direction, which is perpendicular to the magnetic field, then this charged particle will deflect, and the direction of deflection is along the direction of the thumb, like it will move upward direction. Now if you keep the direction of magnetic field fixed, but if you change the direction of the current or the direction of the charged particle in other side, then you will see the deflection is downward. So keep the magnetic field along this direction of the forefinger, keep the direction of the current along the direction of the second finger, then you will find the direction of the motion of the charged particle along the direction of the thumb. This is basically Fleming's left-hand rule. And you see force, thumb direction of the motion or force, forefinger, it is representing the direction of the magnetic field, and second finger, it is representing the direction of the current. So these 3 fingers are perpendicular to each other. Magnetic field, direction of the current, and you will find the direction of the deflection of the charged particle. And this figure clearly represents the angle properly. Is a field, force, and current all are perpendicular. Now let us give one example of the deflection. Like this is the alpha particle. You know, alpha particle is a positively charged, and beta particle is the negative charge, and gamma is uncharged. So in a magnetic field, N to S is a magnetic field always. Mind it, N to S is the direction of the magnetic field. So this is the direction of magnetic field N to S. Like I am keeping this forefinger along the direction of the magnetic field, because this finger represents the direction of magnetic field, and this finger represents the direction of the current. And you see the alpha particle. Alpha particle is positive charge. So the direction of the positive charge is called the direction of the current. So this is the direction of the magnetic field, and this is the direction of the current. Then this is the direction of deflection. So you see alpha particle is it is just moving the perpendicular to the magnetic field. So this is magnetic field, and this is perpendicular to the magnetic field, and this is the direction of the alpha particle. Then alpha particle will move obviously upward direction. You see the alpha particle is moving upward direction. Now I am giving you the example of beta particle. You know, beta particle is the electron, right? And the direction of electron is not the direction of the current. the current is just opposite to the direction of electron or beta particle. Here it is showing the direction of the beta particle. So I will show the direction of current opposite to the beta particle. So this is the direction of magnetic field, and this is the direction of current is opposite to the magnetic field. So the direction of the deflection must be downward. So this is the direction of the magnetic field, and this is the direction of current, because the direction of beta particle is this and the direction of current is opposite. So now it must be downward. So see, the direction of beta particle is downward and the direction of alpha particle is upward, and the direction of gamma particle is a straight line. It is not deflected because gamma particle is uncharged. And these are also example, like cross means magnetic field into the page, and magnetic field into the page, and this is the direction of alpha particle, means the positive movement of the positive charge. Alpha particle is positive charge, it is moving upward. So in that case it is deflecting in the left side, like alpha particle is deflecting in the left side. So it's the magnetic field, and this is the direction of the alpha particle. So this is the direction of the deflection. So say alpha particle, because the alpha particle is considered, the direction of the alpha particle is considered as the direction of the current. Now see the beta particle. So beta particle is moving in the same direction, but we will consider the direction of current opposite to the direction of the beta particle. So beta particle direction upward and current direction is downward. So now the deflection is right side, right side of the page, right? So the direction of the magnetic field and direction of the current, and the direction of beta particle upward. So the direction of deflection is right side of the page, and gamma particle is it is moving in a straight line. Now this is the last example. You see alpha particle, and this is the cross. Cross means the magnetic field into the page, and alpha particle means the direction of the current. So this is the direction of current, and this is the direction of magnetic field. So of course this alpha particle will deflect upward direction, and see this is the example. So cross is the magnetic field into the page, and the direction of the alpha particle means the direction of the current. So direction of the magnetic field, direction of the current. So this is the direction of the deflection. So the alpha particle is moving upward direction. So this is basically Fleming's left hand rule.